Let's take a look now at linear inequalities in two variables. Just like we can talk about equations in one variable or equations in two variables, likewise, we can talk about inequalities in one variable or inequalities in two variables. Just like the inequalities of one variable have a lot in common with equations of one variable, likewise, our inequalities in two variables will have a lot in common with equations of two variables. So here, we start with a definition. What do we mean by that? A linear inequality in two variables is an inequality of the form ax plus by is greater than c, ax plus by is less than c, ax plus by is greater than or equal to c, or ax plus by is less than or equal to c, where a, b, and c are real numbers, and a and b are not both 0. If one of them is 0, that's okay, but they shouldn't both be 0. Because if they're both 0, then you just have 0 is greater than a number or 0 is less than a number. Okay, so that's what we mean when we say a linear inequality in two variables. Notice this looks a lot like a linear equation in two variables. Ax plus by equals to c, but with the equal replaced with either an inclusive, with an exclusive or an inclusive inequality. Okay, now just like when we solve systems, just like when we solve equations of a single variable, you have a single solution. But when you have an equation of multiple variables, of two variables, then you have infinitely many solutions, to the point where we don't list them, we graph them. Something similar will be true for a linear inequality in two variables. We have too many solutions to adequately list, even if we're using interval notation, even if we're using set builder notation. It's not convenient or particularly useful to try to write out the solutions. So instead, we're going to be relying on a graph. All right, so let's go ahead and consider our first example. We're going to graph. We don't usually say solve. However, if we say solve, we generally also mean graph, because our solutions are most conveniently expressed in a graph. All right, so what are we going to graph? Let's begin with the inequality 2x plus 5y is greater than 15. Okay, to graph an inequality, the first thing you want to do is you want to graph the analogous equation. Graph the what equation? Analogous, the one that's like the word analogy, the one that's similar to it, except that instead of a greater than or instead of a less than, it's got an equal sign here. So basically, pretend that this is an equal sign and graph that first. Okay, so step number 1, we're going to graph 2x plus 5y is equal to 15. And that we know how to do. We can solve for y, put this in slope-intercept form, and then graph. So let's go ahead and do that first. I'm going to subtract 2x from both sides. 2x minus 2x goes away. That's 0. Leaves me just my 5y. And that's equal to minus 2x. And since that's a positive, we can say plus 15. Now we can go ahead and divide everything by the number 5 to isolate our y. 5 divides away, and we're left with y. Over here, negative 2 divided by 5. Well, that's negative 2/5 x. And then 15 divided by 5 is just the number 3. So now we can go ahead and graph this. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. We have a y-intercept of 0, 3. Notice when x is equal to 0, anything times 0 is 0. That leaves you just y is equal to 3. So if x is 0, y is 3. Okay. Now I have a slope of negative 2 over 5. Remember how a slope works. The numerator tells you how far up or down you go. Since that's a negative, you're going to go down. And the denominator tells you how far left or right to go. Since that's a positive, you go to the right. Okay, so down by 2 and right by 1, 2, 3, 4, 5. Right there. Down by 2, right by 5. All right. So now we're going to connect the dots. One thing to note is that just like with an inequality of one variable, when you have inequality of two variables, you can have both inclusive and exclusive versions of the inequality. Remember, inclusive are the ones that include that value as part of your solutions. So these are called inclusive. And the equal part is what tells you that it includes that. We want this to be greater than C or equal to C. We want to include the C. But here, we don't want it to equal to C. We want it to be just greater than or just less than. So these do not include the C. So these are exclusive. Whenever you graph an inclusive or an exclusive inequality in one variable, the way you write it is using either parentheses or brackets. Right? If we have something like x is greater than 2, we would write that as 2 to infinity with a parenthesis around the 2. When you have something like x is greater than or equal to 2, we have everything from 2 to infinity, but now we put a square bracket around the 2 to signify that that 2 is included. Well, here we're not going to write this in interval notation. We're going to do it as a graph. So we need a different symbol besides the parenthesis or the bracket that we use with one variable. The way we're going to do it is we're going to modify what the shape of the line is. Whenever you have an inclusive inequality, where you're including the boundary, you're going to use a solid line to connect your dots. However, if you have an exclusive inequality, either greater than or less than without including the boundary, we're going to use a dotted line. The dotted line means you're going to go up to that boundary, but that boundary itself is not included. Okay? So here, when we connect our dots, notice this is an exclusive inequality, greater than, not greater than or equal to. So when we connect our dots, this is an exclusive inequality, so we're going to use a dotted line to connect those points. Like that. All right, so that is our graph. And here, just as a note, use a solid or dotted line as appropriate. Where again, exclusive, use a dotted line, greater than or less than. Inclusive, use a solid line, greater or equal to, less than equal to. Okay, so now that's our boundary. But notice, this is the boundary where 2x plus 5y equals to 15. We don't want 2x plus 5y to equal to 15. We want it to be greater than 15. So what we do now is we need to figure out which side of our line is going to give us our solution. Because remember, with an inequality in one variable, if you have x is equal to 2, on the number line, that's the number 2. Over here, that's the number 2. But then depending on where your inequality is pointed, if it's greater than, you're going to go to the right, or if it's less than, you're going to go to the left. Right? If it's greater than, you go to the right. If it's less than, you go to the left. So over here, you're going to have something similar. If it's this dotted line right here is the boundary of this equation, given by this equation, we want to figure out, okay, which way do I want to go? Now, on a number line, you only have two choices, left or right. But here we have what? Left, right, up, and down. So the simplest way to find which direction we want is to use what's called a test point. So that's our second step. We're going to choose a test point. Now, what's a test point? It's exactly what it sounds like. We're going to pick a point, and we're going to use it to test the inequality. What point do we want to use? Well, it doesn't actually matter. The only condition is, the only requirement is that whatever point you choose should not be on this line. So choose a test point. Make sure it is not on your line from step 1. So any point as long as it's not on this line right here. I like the point 0, 0 because it's easy to work with. Look, 0, 0 is not on the line, so that would be fine. I could also use 0, 1, 1, 1, or I could use 0, 1, or I could choose -5 and -2, or I could choose -5, 1. It doesn't matter. Any point is fine. I could choose something up here if I wanted. I could choose 10, 17 up there. And that's fine. Any point is fine as long as it's not anywhere on this line. So, like I said, I'm going to choose something very simple. I'm going to choose 0, 0. If you want to choose something else, that's fine. It doesn't really make a difference as long as you pick something not on this line. So here, I'm going to choose 0, 0. I choose 0, 0. All right, so now what you're going to do is you're going to take that point that you chose and you're going to plug it into the inequality. Go back to the original problem and plug it in. Step number 3, plug that test point into the inequality. Okay. If you plug it in and you get a true statement, so if true, then you want your solutions are on the points that you want are on the side of the test point. If true, solution set is on the side of the test point. However, what if it's not true? What if it's false? Well, again, there's two choices. You can go this way, you can go that way. So if it's false, the solution set is on the opposite side of the test point. All right, so let's go and do that now. Let me take 0, 0, and I'm going to go and plug it into this inequality. 2x plus 5y is greater than 15. 2x plus 5y is greater than 15. All right, well, my test point is 0, 0, so let me just go and plug in zeros there. 2 times 0 plus 5 times 0 is greater than 15. Anything times 0 is 0. So here that's going to give me 0 plus 0. Okay, that's 0. And I'm left with a statement. I'm left with a statement 0 is greater than 15, which is false. I know that is false. 0 is not greater than 15. Okay, so that was my test point right there. 0, 0. If what I did gave me a true statement, then my solutions would be in this direction, towards 0, 0. Oh, but it didn't. It gave me a false statement. Okay, well then my solutions aren't towards 0, 0. They must be in the opposite direction. So my solutions are all the points up and to the right of this line right here. It doesn't include the line. It's only all the points up and to the right of this line. Just like that. So let's go ahead and give this a try. Go ahead and graph the following inequality. Let's see. Let's have you try 3x minus 2y is less than or equal. Now remember, dotted line versus solid line. You have to watch out for that. 3x minus 2y is less than or equal to, let's say, 8. Right. Go ahead and pause the video, graph that, and once you have a result, go ahead and unpause and we'll go through it together. All right, so let's go and give that a try. We're going to start off by graphing the equation, replacing this with an equal sign. We're going to go ahead and graph 3x minus 2y equals to 8. Here we can find individual solutions and connect the dots, or we can write this in slope-intercept form and use that to graph. It doesn't really matter which way we go about it, as long as we form a graph. So here, let me go ahead and subtract 3x to make this 0, leaving us just minus 2y. Here we have minus 3x plus 8, like that. And then we can divide everything by negative 2, all the way across. This is now 1, so that's 1y. This is a negative divided by a negative, so that's a positive, 3 halves, x. And you have an 8 divided by negative 2, which is negative 4. All right, so we're going to go ahead and graph this line. Note that because this is an inclusive inequality, we're going to use a solid line. So again, note, inclusive inequality. Means we graph with a solid line. If it was an exclusive inequality, then we use a dotted line. All right, so let's form a grid here. We have an x-axis and a y-axis. We have a y-axis, we have a y-intercept along the y-axis of 0, negative 4. So we're going to go down 1, 2, 3, 4. There's our y-axis. When x is equal to 0, anything times 0 is 0. So if x is 0, y is negative 4. And now we have a slope of 3 halves. We're going to go up by 3 and right by 2. 1, 2, 3, right by 2. There's our point. And now we're going to go ahead and connect our dots. And since we have an inclusive inequality less than or equal to, then we're going to go ahead and use a solid line to connect those dots. So here's our boundary. Our answer is going to have this line and everything to one side of this line. Now that we have our line, we want to go ahead and figure out which side of this line we're going to use for our answer. So next we need to choose a test point. It doesn't matter what that test point is, so long as it's not on this line. So we couldn't use this point or that point or any other point along here, but we can use something like 0, 0. We can use something like 0, 1, 1, 0, 1, 1. It doesn't really matter. Try to keep it simple. I like 0, 0 because it's a simple number to use, and as long as it's not on the line, that's a perfectly valid number to choose. All right, so I'm going to go ahead and choose 0, 0. And of course, if you chose something else, that's fine. You'll still get the same answer, even if you used a slightly different point. So now we want to go ahead and plug that in. As our next step, plug the test point into the inequality. So that's a 0 and that's a 0. 3 times 0 minus 2 times 0 is less than or equal to 8. And what we want to do now is check to see if this is a true statement. Well, we can simplify that. That's 3 times 0, which is 0, minus 2 times 0, which is all just 0. And here 0 is less than or equal to 8, which is a true statement. Now remember, if you have a false statement, that means you want to move away from your test point. But in this case, we have a true statement, which means that our answers are going to be toward our test point. So here was our test point, 0, 0. And so our solutions are going to be this line and everything toward the test point. So graphically, we represent that by shading everything in this direction, toward the test point. And there we go. This line and all of these points up and to the left of this line represent the solution set. Note this is how we will be illustrating our answers, mostly because writing something out like this in set notation or writing it in any other notation is difficult. It's still cumbersome, and it doesn't really give us any more information than this graph already does. So we generally leave it like this. So the next thing we want to do is we want to talk about a system of inequalities. Whenever you have an equation, you can graph it and it forms a line if you have a linear equation. When you have a system of equations, you have several lines, and what you want to do is you want to find what they have in common. You want to find the point of intersection. We're going to have something very similar with a system of inequalities, where we're going to take inequalities, graph them simultaneously, and try to find their intersection. But instead of having two lines that might intersect at one point, since we have regions, since we have space that's been shaded in here, then this space might interact with another line or another space and give us something more than just a single point. Right? So we may get more than just one point, like we do with systems of equations, but it still follows the same idea. We want to graph both of them together, and we want to use those graphs to try to find what the intersections, where they overlap. So that is called a system of inequalities. So that's our next topic here. We're going to solve the system of inequalities. In many applications, a system of inequalities, solving a system of inequalities is also called finding a feasible region. Find the feasible region. These are not different tasks. There's simply two different ways of describing them. This is the way it would be described in a math class. Solve the system of equations. We have a system, meaning a collection of inequalities, all at the same time. And we're solving the system of inequalities by finding any solutions that solve all of those inequalities. In an application setting, whether you be in a psychology, sociology class where you're looking at statistics, or whether you be in a business class or in a finance class where you're looking to solve an equation under constraints, what you would have is a feasible region. In other words, you'd have a region where you could feasibly have answers. Oftentimes, you're not looking for a specific answer. Rather, you're looking for a range of answers. Oh, here are all the different possible ways of satisfying my conditions. Right? So instead of looking for a single point, sometimes you're looking for an entire region. Here's all the places where I can operate and still satisfy my conditions. Right? So here, these are two different ways of describing the same thing. We're going to look for a solution to a system of inequalities, or we're going to find a feasible region. And those all mean the same thing. All right, so let's give some examples of solving systems of inequalities, of finding feasible regions. And let's start with the following. And my paper seems to have taken a life of its own. There we go. And let's go ahead and try the following. Consider the system of inequalities 3x plus, let's say, 4y is greater than or equal to 4, and x minus y is less than 3. Okay? Note these are two different inequalities. However, we're going to consider them simultaneously. This is a system of inequalities. It's not enough to find the solution to the first one. It's not enough to find the solutions to the second one. What we want to do is we want to find any solutions that work for both of them at the same time. Thankfully, because this is done visually, that's actually a very simple thing to do as long as we know how to graph each of these on their own. All right, so let's go ahead and do that. This first inequality, I'm going to go ahead and graph. And in fact, let me grab a different color to make this stand out a little bit. Let me graph this first one using, I guess this is orange. We'll use orange here. All right, so this first one, we're going to go ahead and graph the line the way we would up here. We were going to go ahead and graph it as an equation, and then we'll worry about using a test point to find the direction. All right, so I'll call this one line number 1. Okay, so let's see, we're doing line number 1. 3x plus 4y equals to 4. Okay. Let me subtract my 3x over to the other side here. That gives me 4y is equal to negative 3x plus 4. And then if I divide everything by 4, this will give me y by itself. If I divide this by 4, that's negative 3 over 4x. And if I divide this by 4, 4 divided by 4 is just the number 1. All right, so I can go ahead and graph my line. Let's see here. We would have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so we have a y-intercept of 0, 1. When x is equal to 0, y is equal to 1. And then we have a slope of negative 3 over 4. So we're going to go down 3 steps, 1, 2, 3, and write 1, 2, 3, 4, right about there. Okay. So our line, now note this is an inclusive inequality, so we're going to graph our line using a solid line. Whenever it's inclusive, greater than equal to, less than equal to, we use a solid line to signify that. And now we can go ahead and find a test point to determine which side of our line we wish to take our answers from. Let's see here. We'll use a test point. And I usually like 0, 0. Unless 0, 0 is on my line, it's usually a simple enough point to use that I would rather use that one. So let's go ahead and substitute in 0, 0 into our inequality. That'll give me 3 times 0 plus 4 times 0 is greater than or equal to 4. Or in other words, 0 is greater than or equal to 4. Yeah, that's false. 0 is not greater than 4. That's false. And because that's false, that means that here is our test point. Because that's false, we don't want the side toward the test point because that point doesn't work. Well, then it's got to be all the points on the opposite side. So our solution to our first inequality is all the points that are on this line or up and to the right. Like that. Okay. So now we're going to go ahead and graph the second of our 2 lines. And I'll go ahead and do this one in red. Hopefully that stands out enough. I'll call this one line number 2. Right here, this was line number 1 in case the colors are not super clear. This is our first one. Now our second one. All right, well, we're still graphing our line first. We have x minus y is less than 3. We're trying to isolate our y, so let me go ahead and add, we're going to start off with an equation. So let's go ahead and treat it as if it were an equal sign there. X minus y equals to 3. Let's go ahead and subtract the x over to the other side. So that gives me minus y equals minus x plus 3. And then I can go ahead and divide everything by negative 1. That won't change any of the numbers, but it will change all of the signs. This is now a positive y. This is now a positive x. And this is now a minus 3. So we can graph this. Now remember, this is an exclusive inequality. It's not less than or equal to, it's just less than. So for this one, we're going to use a dotted line. All right. Our intercept is 0, negative 3, because after all, if x is equal to 0, y would equal to negative 3. And our slope is 1, which remember is like saying 1 over 1. So from this point, we go up 1 and to the right by 1. And there we go. We have 2 points. We have our y-intercept, and then from our slope, we can go up 1 and right 1. That gives us another point there. And so we can go ahead and connect our dots. Remember, again, this is an inequality. It excludes the line, and so we physically represent that with a dotted line. like that. All right. So now we're going to use a test point. And again, I like 0, 0. Unless 0, 0 is on my line, I would rather use that. Now you say, well, what if 0, 0 is on your line? Well, then just pick some other point. It doesn't really matter what you choose as long as it's not on the line. So here, my test point. Let me choose 0, 0 again, just because I can. And it's an easy enough point to use. So now if my test point is 0, 0, we're going to go ahead and substitute in zeros into the inequality. Right here, 0 minus 0. 0 minus 0 is less than 3, which is true. And 0 is less than 3. So that means that the origin is a valid solution to this inequality, which means that we want the points that are toward the origin. Notice, when it's false, we want to go away from the point. But when it's true, we want to go toward the point. So now we're going to consider our solutions to be everything that's above and to the left of this dotted line right here. All right, so I'm going to go ahead and shade that in that way. Okay, so now our solution to our system. Remember, our system is made up of two inequalities. However, a solution to a system is a solution that is valid for both of the inequalities simultaneously, which means what we're looking for is the overlap. The solution to the system is not just wherever we have any coloring, but rather where both colorings occur simultaneously. Here orange and here red. So if we look at, see where it overlaps, we see it right here. So I'm going to go ahead and do that in blue. I was labeling that. That was 1 and 2. So where they overlap is this solid line right here, and this dotted line over here, and all the stuff in between there. So that region in there is called the solution to the system of inequalities, or in many application classes, psychology, sociology, economics, and physics and such, it would be called the feasible region, because this is the region where you could feasibly find a solution. All right? So there we go. This is our result for our system of inequalities. Looking at another example, one thing to note is when you have a system of linear equations, we generally only look at 2 at a time. However, with a system of inequalities, we actually can look at more inequalities within a single system. So let's look at a system that uses more than 2 inequalities. All right, so let's see here. Our next example, let's go ahead and find the feasible region. Remember, that's the same as solve the system of inequalities. Both languages, both phrases use different language, but are equivalent. They're asking for the same thing. Find the feasible region that's given by the system of inequalities. All right, let's try x plus y is less than or equal to 4. Let's try x plus 2y is less than or equal to 6. Let's try x is greater than or equal to 0. And let's try y is greater than or equal to 0. All right. Here we have 4 inequalities rather than 2. And this may seem like it'll be a lot more complicated, but really it's just more of the same. Right? One thing to note here is that all of these are inclusive inequalities, so for every one of these we'll be using a solid line. All right, so let's go ahead and do that. Here I don't have enough colors to do all 4 of these, so I'm just going to go ahead and label them as 1, 2, 3, and 4. All right, so let's go ahead and do that. Okay, let's begin with the 2 easier ones. Notice that this inequality is only written in one variable. Same thing with this one. This is only written in one variable. Think about what that means with regards to its boundary. Whenever you have an equation x equals to a number, that's just a vertical line. Whenever you have an equation y equals to a number, that's just a horizontal line. Okay, so I'm going to work these backwards. Let's start with number 4. If we have y equals to 0, that's just a horizontal line. Anytime you have y equals to a number, that's a horizontal line. And it's going to cross wherever y is equal to 0. It's going to pass through wherever y is equal to 0. Okay, so let's go ahead and do that. All right, it's a horizontal line where y is equal to 0. Well, that's just the x-axis. All right, if it's horizontal, flat, where y is equal to 0, up here y is equal to 1, 2, 3, negative 1, negative 2, negative 3. At 0, that's the x-axis. Okay, so the x-axis is the line y equals to 0. But remember, we're not really looking for y equals to 0. Let me go ahead and do all these in red. We're not really looking for y equals to 0. We want y is greater than or equal to 0. Okay, so now I need a test point. Now remember, your test point can be any point that's not on the line. Normally I want to use the origin, but in this case, notice the origin is on the line, so I can't use that. All right, so my test point is going to be some other point, and I'll go ahead and choose 1, 1 as my test point. It can be any point I like, so I'm going to keep things simple using the number 1 instead of the number 0. So using the test point 1, 1. Notice I don't have anywhere to plug in an x value, which is fine. That means I'll just use my y value. All right, so right here, my y value is equal to 1. So my inequality is 1 is greater than or equal to 0, which is true. Okay, so here's my test point. It's 1, 1. And since my test point results in a true statement, that means I want to shade up toward that test point. Now, right now, what I'm going to do is I'm going to just draw a little arrow that reminds me that's the direction I want to shade in. In fact, I'll draw a few of them. That way they stand out. The reason I don't want to shade just yet is because I'm going to have 4 of these all at once. And if I shade all of it right now, it's going to be very, very messy. So right now, I'm just going to say, okay, look, these arrows remind me that I want to shade in that direction, but I'm not going to do that just yet, just to keep the graph a little easier to look at. I don't want to have everything so cluttered early on in the problem. It'll be hard to read it later. Line number 3 is going to be very similar. I have just the x variable. Okay, well, that's going to give me a vertical line. When you have x equals to a number, that's a vertical line. And in this case, it's the y-axis. Because over here, x is equal to 1, 2, 3, 4, 5, negative 1, negative 2. Oh, x equals to 0 right here. That's the y-axis. So let me go ahead and get this line drawn. I'm using a solid line because all of these are inclusive inequalities. And now, again, I can't use 0, 0 as my test point because this line also crosses through the origin. But I can use 1, 1. So there's my test point, 1, 1. And now, there's nowhere for me to plug in a y value. All right, well, that's fine. Let me just use x. That's the number 1 right here. So 1 is greater than 0, which, just like before, that gives me a true statement. So that means that I want to shade toward the test point. All right, so here was my test point, 1, 1. And from this line, I want to shade toward the right, toward that point. So again, I'm going to put a couple of little arrows here to remind me that's the way I want to be going. But I'm not going to shade just yet because, again, that will make my graph very, very cluttered all at once. I'll do the shading at the end. Okay. My line number 2. Okay, well, now this has both variables, so this is going to look more like the problems we've been seeing. If I have x plus 2y is equal to 6, x plus 2y is equal to 6, that's going to give me a line which, if I isolate my y variable, I can go ahead and graph using the slope-intercept form. Let me subtract x from both sides. That leaves me my 2y where it is. This x is now a minus x over here, and that's a positive 6. And now if I divide everything by 2, that gives me y. That is now negative 1/2 x. That's a negative 1 divided by 2, negative 1/2 x. And then 6 divided by 2 will give me a positive 3. So I have a y-intercept of 0, 3. Because if x is equal to 0, I have y is equal to 3 right there. So we'll start with that point, 0, 3. And then we have a slope of negative 1/2, which is negative 1 over 2. All right, so that negative 1 tells me from this point I'm going to go down 1. And then that's a positive 2, which tells me to go to the right by 2. So down 1, right by 2. And that'll put me right there. All right, so now I'm going to connect my line. Something like this. And again, because these are all inclusive inequalities, they're all going to be solid lines, like that. Okay. So now I need to find a test point. In this case, I can use 0, 0, because notice 0, 0 is not on this diagonal line. Now I can continue to use 1, 1. It really doesn't make a difference. So here, let me use 1, 1 still. My test point, I'm going to substitute in 1, 1. So going back to our inequality, we have 1 plus 2 times 1, right? That's my x, plus double my y, and that's going to be less than or equal to 6, which is true. 2 plus 1 is 3, and 3 is definitely less than 6. So 1, 1 is a valid solution. That means I want to shade toward that point right there. So let me go ahead and draw these little lines right here. I'm going to draw 3 little arrows to show me that I want to shade in this direction toward this point. Okay? If that had been false, well, then I'd want to shade in the opposite direction. But this is true, like that. And finally, our line number 1, we have x plus y is equal to 4. We can graph this one if we simply subtract x over to the other side here. That gives me y equals negative x plus 4. And so here I have a y-intercept of 0, 4. When x is equal to 0, y is equal to 4. 0, 4. And I have a slope of negative 1, which you can think of as being negative 1 over 1. All right, that was negative x, which is negative 1 over 1x. So from this point, I can go down 1 and then right by 1. All right, negative 1 over 1. From here, I can go down 1 and right 1. And so if I connect my dots, you can use a solid line to connect those, like this. All right, so now I need a test point. And again, I can use any point I like. And since I've already used 1, 1 for almost everything else, let me continue with that one. My test point will now be plugged in to the first inequality. And that'll give us 1 plus 1 is less than or equal to 4, which is true. 1 plus 1 is 2, which is definitely less than 4. So because that point gives me a true statement when I plug it into that first equation, or that first inequality, that means that this point is a solution to that inequality of our system. And so we want to shade toward that point, meaning this way from the diagonal line, toward that point over here. All right, so now we've graphed all 4 of our lines, and we've shown that we want to be to the right of this line, above this line, down and to the left of this line, and down and to the left of this line. So that gives us this region in here. This 4-sided region is the region where you are satisfying all of your conditions, all of your inequalities, all at the same time. So everything to the right of this line, above this line, down and to the left of this line, and down and to the left of this line. So you have a 4-sided region, 1, 2, 3, 4, and everything inside. Note that when we graph a feasible region, when we graph a system of inequalities, it doesn't make it any more complicated to graph more inequalities. We simply have more individual inequalities to graph. Meaning, if we added more of these, it wouldn't change how complicated these are. We would just have more of the same within that problem. Right? It doesn't make any of the steps more complicated. It just requires us to do that step more times. And this is our result. So as our last problem here, go ahead and give this a try. You're going to go ahead and graph the system of inequalities. You're going to find the feasible region. Same thing. For the following system. Here you have 3 inequalities. Go ahead and graph the inequality, system of inequalities. X minus y is less than or equal to 2. X plus y is less than or equal to 2, like that. And x is greater than or equal to 0. So go ahead and pause the video and give that a try. Go ahead and graph the following system. You graph each one individually and then find where their overlap is. Once you have the graph of the solution, once you have the graph of the feasible region, go ahead and unpause and we'll confirm it together. All right, so let's give this a try. Let me go ahead and graph, I'll call this one number 1, number 2, and number 3. Again, the labeling is just so that you can keep track while you're taking notes. In reality, you don't really need to graph them with a label like that unless you really want to, and it helps you keep track. All right? So here we go. This first, let me start with the last one because it is the simplest. In fact, it's the one we saw already. Whenever you have x equals to a number, that's a vertical line. And in this case, x equals to 0, that's a vertical line through the origin. All right, so x equals to 0. The vertical line x equals to 0. And now we want everything that is on one side of that vertical line. Okay, I'll label that as line number 3. All right, well, we need a test point. Can't use 0, 0 because that's lines going through the origin, so we can use maybe 1, 0 or 1, 1 or really any point as long as it's not on this line. So for my test point, I think I will choose 1, 0 because that's definitely not on that line. And I think I'll stick with that point throughout the whole problem, unless there's some line that goes through it. All right, so I'm going to test 1, 0, and I'm going to do that by simply substituting in. Notice right here I have no place to put in a y value. So I'm just going to plug in my x value, which is the number 1. So 1 is greater than or equal to 0, which is true. So from this line, I want to shade toward that test point, which means from this line, I want to shade toward the right. Okay, now let's take a look at our line number 2. The one I've labeled number 2 here is x plus y is equal to 2. I'm graphing the boundary first before I graph the inequality. And here I can simply subtract x to the other side to give me y by itself. I've subtracted this, so that's now minus x. And since that's a positive, I can say plus 2. Now, when I say negative x, that's the same as saying negative 1 over 1. Right? Negative 1 is the same as negative 1 over 1. So this gives me a y-intercept of 0, 2. And a slope of negative 1 over 1. So I'm going to go down 1, right by 1, right there. And now I can go ahead and graph my line. And since this is an inclusive inequality, just like this other one, we're going to use a solid line for those. Exclusive inequalities use a dotted line. Inclusive ones use a solid line. There we go. And now I need a test point. I will continue to use 1, 0 because it looks like that's not on my boundary. That's not a point that is on the line that I just drew. It's below that. So my test point, 1, 0. And let's see what happens when we plug that in. Let's see, that's 1 plus 0. And that's going to be less than or equal to 2. That's true. 1 is less than 2. So that means that from this line, we want to shade toward the test point. Okay, so this way, down and to the left. We're going to do the same thing to this first inequality. We're going to start by graphing the boundary of x minus y equals to 2. We can go ahead and subtract the x over this way. Keep in mind that's a positive 2, so we can write that as a plus 2 here. And then we can go ahead and divide everything by a negative 1. This changes this to a positive, changes this to a positive, and changes that to a negative. So now we have a y-intercept of 0, negative 2. When x is equal to 0, that goes away, and y is equal to negative 2. So that's my point down here, 0, negative 2. And I have a slope of 1, which is the same as saying 1 over 1. So from this point, I can go up 1 and to the right by 1. All right, so I can connect my dots using a solid line. That gives me the boundary to my next inequality, something like that. And now I need a test point. Again, I've been using 1, 0, and it looks like 1, 0 is not on this line either. So I can continue to use that. If I substitute that into these points here, if I substitute these into these variables here, x is equal to 1 minus y is equal to 0. And we're saying 1 minus 0 should be less than or equal to 2, which is true. 1 minus 0 is 1, which is definitely less than 2. So that's a true statement. If it was a false statement, we want to shade down and to the right, away from the line, from the point here. But since it's true, that means we want to shade up and to the left, toward the point. When it's false, you shade away from the point. When it's true, you go toward it. So here we want to go up and to the left, toward that point. And now, it seems pretty apparent where our feasible region is. We want everything that's to the right of this line, that's up and to the left from this line, and that's down and to the left from this line. So it's got to be that our feasible region is this triangular region here. Our solution to our system of inequalities, our feasible region, is this triangle and all the space inside. And so that's it. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.